Hello friends and welcome to another episode of Beacon Bin Science. Just one question I want to ask you. Have you ever imagined a material that looked like a sponge but in nanoscale, which is having a millions of pores in it? These pores are capable of holding, let's say, drugs, gases, liquid, or even metal ions. Have you imagined anything like that? No, this is not a science fiction, but this is a real world of metal organic framework, which is commonly known as MOFs. In 2025, three scientists won a Nobel Prize in chemistry, and these three scientists were working in the metal organic framework, that is MOF. So in this video, we are going to discuss what are MOFs, why they are so important, what are their roles, and what are the future expectations from these MOFs. So let's uncover the world of MOFs one by one in nanoscale. So let's start from the basic. MOFs or metal organic frameworks are crystalline metals made of connecting metals ion or metal clusters with organic linkers. To understand what are MOFs actually, let's take this example. Consider this as a metal ion and this as an organic linker. Suppose these two are connected and with that linker another metal ion is connected. In this way the 3D structure is forming. That's how they get linked in a real world. Imagine metal ion as joint and organic linker as sticks connecting those joints to form a 3D porous network. That network has a huge surface area and plenty of tiny holes, perfect for trapping and storing molecules inside. If we just take a 1 gram of these MOF, let's say in a real world example, ZIF8 MOF, which is very common. If we just take a 1 gram of this ZIF MOF, the surface area is so large that it can cover an entire football field with just 1 gram. Imagine how porous it is. MOFs has been under development for decades, but they gained a huge leap forward in recognition in 2025. The Nobel Prize in Chemistry 2025 was awarded to Susumu Kitagawa, Richard Robson, and Omar Yaghi for their development of MOFs. But why them? Because they pioneered stable, tunable, porous MOFs that can store gases, trap toxins, harvest water from air, and much more. Their work has led to the creation of tens of thousands of MOFs variants, opening up new possibilities in material science. Now let's see how MOFs are synthesized. The synthesis of MOFs is quite simple yet fascinating. Researchers mix metal salts like zinc nitrate, copper acetate, or iron chloride with organic linkers such as imidazole, terephthalic acid, or trimesic acid in a solvent. Then they heat the mixture and voila, a crystalline MOF forms. This process is often done via solvothermal or hydrothermal synthesis. For example, when zinc ion like zinc nitrate are combined with 2-methylamidazole, you get ZIF8, one of the most studied MOF in drug delivery. Now you might be wondering what make these MOFs better nanocarriers compared to liposomes or compared to polymeric nanoparticles. And the answer is number one, it has a high porosity and surface area. MOFs can hold a large amount of drugs molecule in their pores, meaning higher drug loading capacity compared to many traditional nanoparticles. Number two, it has a tunability. By simply changing the metal center or organic linkers, scientists can design MOFs with different pore size, stability, and drug releasing rate. Number three, it has a biodegradability and biocompatibility. Many MOFs, especially those made of zinc or iron, degrade safely inside the body, releasing the drugs without causing toxicity. Some MOFs are designed to release drugs in response to pH change, temperature, or enzymes, a property highly useful in targeted cancer therapy. Some of the examples of MOFs in drug delivery. Let's make it more concrete with some real examples. ZIF8, that is used for cancer therapy. Researchers have loaded doxorubicin, a common anti-cancer drug, inside ZIF8 nanoparticle. Since ZIF8 is stable at normal physiological pH, that is around 7.4, but dissolved in acidic environment like inside tumor cells, as tumor cells environment is acidic compared to normal cells. It releases the drug only inside the cancer cells. Because of this, results into a targeted drug delivery with minimal side effect. Another example is iron MOF, Fe-MOFs for combined therapy. Iron based MOFs can carry not just drugs but also enzymes or photosynthesizers. For example, iron MOF loaded with curcumin and photothermal agents can combine chemotherapy and photothermal therapy, killing cancer cells more effectively. Another example is UIO66 and MIL101 MOFs. These are zirconium based MOFs known for their exceptional stability. They have been used to encapsulate antibodies and proteins for slow and sustainable drug release, useful for chronic infections or inflammations. Taking one step further, let's talk about nanomorphs. Now, when morphs are prepared at the nanoscale, they are called nanomorphs.
But why nanoparticles is important? The size of the nanoparticles is roughly in between 50 to 200 nanometer, and this is a perfect size to take advantage of EPR effect, that is enhanced permeability tension effect, that allows the drugs to get accumulated inside the cancer without going into the healthy tissues.
EPR effect means that tumor tissues have leaky blood vessels and poor lymphatic drainage, which allows nanoparticles to accumulate more in tumor than in normal tissues. So, nanoparticles passively target tumors, not because they know where to go, but because of tumor blood vessel structure. Nanomorphs combining the porosity of morphs with the mobility and targeting ability of nanoparticles, making them next generation drug carriers. Morphs can make even more smarter morphs by surface modification. To improve targeting and biocompatibility, scientists modified the surface of nanomorphs. Let's see. For example, coating morphs with PEG, polyethylene glycol, improves blood circulation time. Also, conjugating folic acid or antibodies on the surface allows the morphs to specifically target cancer cells that overexpress those receptors. This means the drug loaded morphs go exactly where they are needed, minimizing side effect and improving treatment efficiency. Of course, it's not all perfect yet. There are still challenges like long term toxicity studies, large scale reproducibility, and the stability of the morphs in biological fluid. But the potential is huge. Morphs are already being explored not just for drug delivery but also for biosensing, catalyst imaging, and even gene delivery. In the future, we may see multifunctional morphs that can simultaneously diagnose, deliver drugs, and monitor treatment all in one nanoparticle system.
So in nutshell, MOFs are highly tunable, highly porous, and smarter nanocarriers that are changing the way we think about drug delivery. From ZIF6 to UIO66, these materials are a perfect example of structure, stability, and functionality. These materials truly deserve a seat in a next generation nanomedicine field. If you also think the same, hit the like button. Also, if you find this video informative and interesting, please share it with your friends and family because sharing is caring. See you in the next video.